Yeah.
Fusing enhanced lightweight CNN for culturally relevant food classification, advancing assistive technology for visually impaired Nigerians. The work was done along with a co-researcher, Aliu, Abiu,
The voice is not
who
clear.
reside
Please,
in the
louder,
Department of
please.
Computer Engineering, Federal Polytechnic, Ilaro, Nigeria. These are the outlines of our work, introduction down to the references. Introduction. Visually impaired Nigerian faces challenges identifying local foods due to gaps in current assistive technology. AI continues to improve quality of life for disabled individuals, especially in healthcare, navigation, and object recognition. Engineers are now creating automatic food classification system to aid food identification for the visually impaired individual. Then the system enable people to become aware of what they eat and support self-sufficiency, that is the system at hand. CNN are effective for visual classification but fall short for Nigerian specific food items. Most of the foods that are used on the CNN algorithm are non-Nigerian foods. And the research
Please go to the data
advances
set.
what we have done before that has been presented by trying to see how we can improve on it with the extension to the fuzzy logic approach. Due to issues with generalization, flexibility, and model size, new architectures like custom convolutional fuzzy neural network and mobile net were introduced in this study. And also the augmentation of data by 30% was equally introduced to check the effects of the system. Literature review. The research addresses a critical gap in assistive technology for visually impaired Nigerians by proposing culturally adapted food classification system using lightweight convolutional neural network. Note, existing systems including the automatic food classification model often rely on Western data sets and are ill-suited for classifying indigenous Nigerian foods. The study therefore introduced a custom convolutional fuzzy neural networks integrated with fuzzy logic to enhance performance, explainability, and efficiency. The major weaknesses in the literatures include weak generalization, heavy computational demand, and poor adaptability. All these were addressed through model redesign, and data augmentation. The proposed CCFNN and the benchmarks models like MobileNet and the LeoNet 5 were chosen for their lightweight architecture and compatibility, which resource constrained environments. These, these
Please move the
initiatives
next slide.
promote
Please move the next slide.
inclusivity, particularly in underdeveloped regions, by developing culturally relevant AI solutions, and it further aligns with global AI ethics, emphasizing local data control, sustainability, and deployment feasibility on mobile devices. Methodology.
Okay, next slide, please.
The study
Methodology.
used a data set of 4,000 images representing 20 Nigerian food types across freshness stages. Each image is resized to 100 by 100 by 3 RGB to standardize the inputs. Therefore, data augmentation was applied on 30% of the dataset using rotation, flipping, translation, zooming, and shining to test the robustness of the system. Besides, multiple performance metrics evaluation were also applied, and this includes accuracy along with precision, recall F1 score, ROC, AUC measurement, and training time and parameter numbers. Free models that were used and evaluated include the proposed custom convolutional fuzzy neural network, which is the novel model featuring fuzzy Gaussian activation layers. 2. Mobile net, a depth-wise separable CNN for efficiency. Then LueNet, a classic compact CNN architecture. Figure 1 is the architecture of the
Please change the slide, please.
CNN-based full classification system as a pointer to the current study. And figure 2 shows few samples of the data sets that were used to develop the model. All experiments were conducted on the Lenovo T480X, and the performance was measured using accuracy, precision, recall F1 score, AUC, ROC, training time, and parameter count as stated. These are the results of our work. Table 1 shows the result of performance metrics. The model in the first column, augmentation, validation accuracy, test accuracy, F1 score, prediction, precision, recall, AUC to ROC, then the number of parameters that each model possesses. The NO indicates that when no augmentation was applied and the values acquired at that level, and when 30% augmentation was applied. It is so for all other models. And from the results so far, accuracy from our proposed CCFNN model, the accuracy achieved is 95.2%. This is it. %, and the AUC to ROC of 99.82%. Then the training time was 850 milliseconds, and parameter count is less than 30,000. And when it was done with augmentation of 30%, the accuracy dropped to 80.9%, and the AUC to ROC was 99.58%. Note from the results, mobile net yielded similar accuracy of 95.7%, but with 4.2 million parameters, making our proposed CCFNNN models to be significantly more efficient. And in contrast, the model initially published, AFCMs, has an accuracy drop to 37.4% under augmentation, demonstrating its inferiority with generalization after augmentation. So our proposed model,
why is this not clear, please?
fuzzy logic layers enhance feature sensitivity and interoperability, making it more suitable for real-time assistive application in visually impaired context. Furthermore, CCFNN's adaptability to indigenous food items presents a clear cultural advantage over generic Western trained model, as we can also see from table 2, the implication of 30% augmentation with responses. This table is to review what happened during augmentation of dataset with 30% on each model. Our proposed model do not require augmentation, and this table is reflecting that, because after 30% augmentation, there was a late delivery in terms of stability, and it learned very slowly, and it requires a lot of parameter tuning. These are the graphical results revealing the behavior of model during training when without augmentation and with augmentation. The first one is the accuracy, where the second one is the loss, uh, training, validation, and all that. And the second one there is the mobile net for augmentation and no augmentation, followed by the already published one in our previous work, which is AFCN, accuracy and loss, and LeoNet, accuracy and loss, with and without augmentation. In conclusion, the study confirms that lightweight CNN integrated with fuzzy logic can provide effective, accurate, and efficient food classification for visually impaired Nigerians. So CCFNN outperforms prior models while remaining feasible for deployment in low resource environments. Our recommendations. Future work should explore fuzzy pooling and quantization to reduce computational demand further. Real-world deployment via mobile apps should be piloted in rural communities. Expansion of other culturally specific data sets are equally encouraged to increase impact across regions. And it is equally good to promote real-world use with explainable AI and localized testing in Nigerian communities for scalable assistive solutions. These are our references. Thank you.